Hello, my name is Evan, and my team members Nat and Anna are here to present our IC engine presentation for ME4056. In this presentation, we will go through the background and introduction, major milestones, the experimental setup, the results from Experiment 1 and Experiment 2, a preview for Experiment 3, and the conclusions we can draw. The system in question is a 4-stroke engine attached to a 48-volt regenerative motor. Using this, testing and analysis will be performed across 3 different experiments to determine various engine parameters. These will consist of mechanical, fluid, and control properties. The main goal is to characterize engine input and output of the IC engine system using the work equation shown. This will be done by conducting 3 different experiments. In Experiment 1, the head is removed from the piston and there's no injected air. Using this, the parameters found are the work of the motor, the work done by friction, and the rotational inertia. In Experiment 2, the head will be added to the piston, and the new parameters found are work of air and the work discrepancy term. In Experiment 3, the head is still on, and there is now injected air to simulate combustion. Using this, the work air term and our work discrepancy term will be updated accordingly. The experimental setup has 2 different sensors, a digital encoder and a force transducer. The encoder measures the position of the piston, and the force transducer measures the torque on the motor. There's also flywheels at the end of the engine that can be added or removed to modify the rotational inertia of the system.
For Experiment 1, we begin with the total flywheel energy balance, and then canceled terms not relevant for our experimental setup. The work of the piston is assumed to be negligible due to the high flywheel inertia and relatively long period of time, or angle, over which the data was collected. Also, without the piston head attached, there is no work being done by air, making that term equal to 0. By getting rid of these terms, we get the simplified energy balance shown here. When we consider only the portion of our test run at steady state, we can easily find the friction and motor work, since they become the only terms left in the equation and are therefore equal to the negative of the other. When we consider the test run in its entirety, from rest to steady state, we can solve for the inertia of the flywheel, denoted here as I subscript fly, using our value of friction work determined from steady state analysis and calculating the motor work over the entire run. This figure provides a good visual representation of the work of friction and the work of the motor when the flywheel moves from rest to steady state velocity. Frictional work was found by multiplying friction torque, which is the same as the steady state motor torque, by the entire angle range covered, and motor work was found by numerically integrating motor torque across the entire angle range. The values calculated for the flywheel inertia, which consisted of 3 flywheel masses, are shown in the far right column of the table and can be compared to the theoretical value shown at the bottom. 2 possible sources have been identified for potentially causing the discrepancies between the theoretically and experimentally calculated inertias. The first is engine wobble, which results in the very noisy signal seen in the steady state region of the plot, and leads to less accurate calculation of friction and motor work terms, and thus also of flywheel inertia. The other is that the experimental inertia value encompasses the inertia of the motor shaft, leading to a greater value than in the theoretical calculation, which only considers the flywheel masses. Another finding of this first experiment was that the engine motor system follows the Newtonian rather than the Coulomb friction model. This means that engine RPM and resulting friction torque have a linear relationship instead of friction torque being independent of RPM. This applies to future experimentation in that the same friction torque can't be used in calculations for different engine speeds, but can be found for a given engine speed using the linear fit shown here. The last finding from Experiment 1 was that the engine motor system follows Newton's second law of rotation, torque equals inertia times angular acceleration. This is shown very clearly on these 2 graphs, where increasing inertia by adding more flywheels to the motor shaft resulted in an increase in the time necessary to reach approximately the same steady-state angular velocity. In other words, when steady-state torque stayed constant and inertia was increased, angular acceleration decreased, which follows the theory.
Experiment 2 was focused on characterizing the work of the air. This was performed by placing the head back on the engine but not injecting any air. Note that the work of the piston and the discrepancy work are still assumed to be 0 for the reasons previously mentioned by Anna. Some other things about this analysis are that work of the motor, work of the friction, and inertia of the flywheel are already known from Experiment 1. As a result, the work energy equation simplifies, where work of the air, denoted in red, is the only unknown. From there, if the expansion stroke is analyzed, work of the air can be solved for one of 2 ways: theoretically, with equations that are shown on the next slide, or experimentally, by solving for work of the air in the simplified work energy equation. It should be stated that an adiabatic expansion assumption was made because of how quickly the power stroke occurs. The same assumption won't be made in experiment 3 since air will be injected. However, since, once again, no air is injected during experiment 2, this assumption can be made. One expectation for no pneumatic injection is that the work of air during the power stroke is the negative of the work of air during the compression stroke, which comes in handy for the actual calculations. Calculating work for compression is much easier in this situation given that all pressure values are simply 1 atm. In calculating the theoretical work done by air, some thermodynamics is involved by integrating pressure over the change in volume in the cylinder. This expands out to several different terms as seen here, where gamma is 1.4 for our experimental conditions, pressure at bottom dead center is equal to atmospheric pressure, and volumes at top and bottom dead center are calculated from dimensions that were measured during experiments 1 and 2. The final result reached for the theoretical work of the air was about 14.1 joules. The process for finding experimental work of air was a bit more involved. Several tests were ran with varying speeds and different flywheel inertias. The experimental work of air was found for each test, as stated previously, by solving the simplified work-energy equation for work of air. However, in an effort to obtain more accurate results, the equation was solved for each stroke, then averaged across multiple strokes for each engine stroke, i.e. intake, compression, power, and exhaust. The important ones to consider are compression and power, for which the calculated values are listed in the table. One thing to note is that only some of the results follow the expectation that work of air for the power stroke is the negative of the work of air for the compression stroke. Furthermore, attention should be drawn to the fact that the theoretical work of air is only a function of pressure and volume, yet in the experimental results, it can be observed that work of air changes with both engine speed and inertia. These deviations from our expectations can be attributed to a few factors. First, there is noise in the data. Noise can explain the changes in work of air with engine speed. When holding the inertia constant, the magnitude of change in the work values isn't that large. A much larger magnitude of change can be seen between the work values of the two inertia settings. This is mainly due to the fact that with low inertia, work of the piston comes into play, which we assume to be zero. Therefore, with better signal processing such as using a fast Fourier transform and better modeling assumptions, the results in the table should more accurately meet our expectations. Here are the plots for the results in the table from the previous slide. These plots depict some of the issues mentioned before in the data. With higher inertia, there is energy exchange between the flywheel and air, which causes the motor's peak torques to be smaller, so the magnitudes of the torque peaks are on the same level as the noise. With lower inertia, this is only a problem as engine speed increases, but as seen in the case of slow engine speed and low inertia, the peak torques are easily distinguished. The opposite is true for the same engine speed with the higher inertia. The importance of finding both theoretical and experimental work of air is to compare them in order to characterize the accuracy of our assumed model. This is where the discrepancy work term comes in. By comparing work discrepancy to the uncertainty of the work of air, which is equal to the uncertainty of the work of the motor, we can determine whether the modeling is inaccurate. If it lies outside the bounds of the experimental work, we know the sensors are good enough, but our modeling isn't accurate because of our assumptions or other unmodeled effects. However, if work discrepancy lies within the bounds, it's difficult to distinguish between uncertainty and modeling discrepancy, so the modeling can't be deemed accurate or inaccurate. Once the work discrepancy and uncertainty values are calculated for each case, the logic explained on the previous slide can be applied to determine whether or not the modeling for the particular engine speed and inertia setting is accurate. According to the table, since all of the work discrepancy terms are larger than the uncertainties, the sensors are good enough and all of the modeling can be considered inaccurate because of assumptions we made or other unmodeled effects. One interesting thing to note is that the work discrepancy terms for the lower inertia settings are much greater than their respective uncertainties, compared to the work discrepancy terms for the higher inertia settings and their respective uncertainties. This reflects our poor modeling. For example, not accounting for work of the piston when it indeed does play a role for the lower inertia cases.
Looking to experiment 3, the work of the engine at full braking load will be found by adjusting the timing of air injection and desired motor speed. The reason we inject air is to simulate combustion like that of an actual IC engine during a power stroke. To find the work air term, we will use the same experimental procedure as in experiment 2, but it will encompass the work due to the additional pressure from injected air. Using this term, the only unknown is the work discrepancy term, which will be evaluated with regards to uncertainty and determine if the engine motor system follows our modeling under operational conditions. From the 3 experiments, we will have characterized the engine mechanical properties, evaluated system performance under full braking load, and determined how well our model was followed during both non-operational condition and operational condition. Thank you.